need not exist of the trial function. Right? So this is not defined, for instance, for piecewise linear functions, which we're going to use a lot in finite element approximation. Okay, so bad news here. This is not defined for piecewise linear functions, for instance. Piecewise linear functions. Okay. So here's a piecewise linear function, which we might use as a trial function. Okay, something like that. And then we can still, we can compute the first derivative, no problem. It's not differentiable, of course, at these nodes here, but we can, this is now under an integral sign here, so we can break up the integral into pieces and then still compute all these expressions. So it's all well defined. The first derivative is, if I draw here the first derivative, okay, it's here, then it goes down, and then it goes negative in the third step, and then goes up a bit. Okay, so this would be the first derivative, but we cannot form the second derivative. So what do we do? Well, the solution is easy because we can use integration by parts to reduce the number of derivatives on the trial function. Okay, so solution to this issue, use integration by parts. This is going to be a technique we're going to use a lot. Integration by parts, so that turns the differential equation here into an integral equation of this form. So we take the left-hand side here, multiply by an arbitrary function, v, I'll call it here, and then integrate over the interval. Okay, there must still be 0, of course, and now we can use integration by parts. I'll write IBP for that, integration by parts. It comes this, minus u prime, and then one derivative goes on the v, plus u v. We cannot do anything with the other terms because they don't involve derivatives. Plus x v dx plus u prime v 0, 1. Okay? This v here is an arbitrary test function. It plays the same role as the weight function here, but it's called a test function in this context. V, a test function. Okay. Now it's clear that if a solution, if a function satisfies this equation, then it satisfies this integral equation as well. We've done this. We've proved this. But the converse is not necessarily true. If a function of u satisfies this for certain v, if the integral is 0, it doesn't necessarily mean that the integrand, that whatever multiplies the v, is 0, of course. However, if this is true for many v's, then we expect equivalence between the two. Okay? So if this was true for all v or for sufficiently many, then you would have equivalence, and then you get what is called the weak formulation. Weak because it requires only a first derivative of the function. So here's the weak formulation, and this, by contrast, is called then the strong formulation, the BVP, boundary value problem. And that's a strong formulation, and this is the weak formulation of the same problem. So what is it? It's then this integral equation minus u prime v prime plus u v plus x v dx plus the bounded term u prime v 0, 1, and together with the boundary conditions. Equals u1. And then for all v, okay? And this must be 0, of course. Now it turns out that it's sufficient if this holds for all V that satisfy the homogeneous form of any Dirichlet boundary conditions, turns out. And that's what's usually taken all V to mean. So all V is usually taken to mean and I'll write this down because it's a technical point. All functions V that satisfy the homogeneous form of any Dirichlet boundary condition. Dirichlet boundary condition means the boundary conditions are imposed on U directly, not derivative boundary conditions. BC is boundary conditions. So what does it mean? It means that if you had a boundary condition on the U, so if you had this Dirichlet boundary condition, U, which is inhomogeneous, right hand side is non-zero, okay, then you would impose the condition V0 equals 0. So the test function would then satisfy the homogeneous form of that boundary condition. If your boundary conditions were both derivative boundary conditions, if you had this as boundary conditions for the problem, okay, then you would have no boundary conditions on V, because there are no Dirichlet boundary conditions in this case. Then you wouldn't impose any boundary conditions on V. Then no boundary conditions on V need to be imposed. Okay, so that's a technical point. Of course, the more V you allow, the easier you see will be the equivalence between weak and strong formulation. But you can go down as far as this. Okay, and then so the result then is that you have equivalence between weak and strong formulation. At least for sufficiently smooth functions, but, and this is the purpose of all this, the weak formulation only requires the first derivatives to exist, so it allows a much larger class of trial functions to consider, to construct approximate solutions. And of course, in general, we won't have the exact solution. We are interested in approximations, and the weak formulation allows us to choose approximations in a much wider class of functions, including piecewise linear functions. Okay, that's the whole purpose.